Hello, today I'm going to walk you through the workflow and the core of my paper manuscript, which are related to meningitis prediction using ensemble learning. The reason of this research is that it's challenging that clinicians differentiate meningitis and non-meningitis cases if patient shares some similar symptoms or features in the same of ER. Hence, we explore the potential of machine learning to assisting in meningitis detection using mimic-free EHR dataset. From the raw data here, we moved into a crucial phase called data preprocessing. This is where we clean and structure our data to make it usable for our models. This involves several steps, including data cleaning, feature engineering, undersampling, shuffling, and lastly, we filtered out the first meningitis diagnosis for each patient and excluded subsequent records to ensure temporal purity. This process yielded 214 meningitis cases, while 46 303 non-meningitis samples admissions without any meningitis diagnosis were included as controls. After data preprocessing, our data is split up into two parts. A larger portion becomes our training set here, which we will use to train our models. The rest is divided into two testing sets, which we will use to evaluate how well our model performed on unseen data. Furthermore, testing set 2 was created with 34 non-meningitis samples with at least 2 related features from top 100 important features, since we aim to build up a harder diagnostic condition that simulates real-world ER scenario. Let's move to the section of model training. Firstly, I trained random forest, light, GBM, DNN separately. What you see up here of the 5-fold cross validation outputs of these three models: AUC, sensitivity, PPV, MPV, and F1 score are being used for performance eval. The reality here is that the performance of each model is quite short of hitting my initial expectation. For example, the sensitivity of random forest here is only 7278, PPV 0.8066, MPV 0.7548, resulting F1 score 0.7623. The similar things happen in light GBM and DNN here. That has led me musing about coming up a new way to bump up the results. I was wondering whether there is an algorithm that is able to improve the ultimate outputs based on these three models. This is where ensemble learning comes into play. In the process of ensemble learning, I leverage a technique called stacking to combine the predictions from these three models to a more powerful meta model. This meta model takes the output values of three base models as input values. It ended up getting solid outputs on both two testing datasets. On the screen, we can see the AUC of testing 1 is 0.9637, sensitivity 0.9690, specificity 0.8790, PPV 0.8896, MPV 0.9660, and lastly, F1 score 0.9266. They are pretty good values, isn't it? So, sensitivity is the most improved metric, where has been increased over 20% than the values in the base models. So we can compare the base model sensitivity here is they are all around 72%. So it did improve a lot. The result of testing 2 is slightly lower than testing 1 set, but still robust. That proves ensemble learning is capable of creating a single more powerful meta model, aka strong learner, while combining basic models, aka weak learner in this case.